Hello everyone. So let us discuss the first law of thermodynamics in this first part of thermodynamics video discussion. So I welcome you all in our channel 361 physics. Okay, so let us begin our discussion from here. So first law of thermodynamics. So so zero law of thermodynamics basically it defines the temperature because uh, the flow of heat energy is determined by the temperature, and if we bring the object in thermal equilibrium, then there is no flow of heat. That actually gives the idea of the temperature. That's why we say this zeroth law of thermodynamics defines the temperature. Later on, here comes the first law of thermodynamics, and this first law of thermodynamics is basically useful in determination of the energy, and basically it deals with the conservation of energy. So first law of thermodynamics defines how the energy conservation is preserved even in the different kind of gaseous system. Okay, so basically in this first law of thermodynamics we will be dealing with different kind of system and the work done by the gas in different kind of system. So first of all, let us talk about the different type of systems. Okay, so but before that I like to make you clear about the system is something that is under our study, that is under our investigation observation. So basically if we have some container and that container consists of some gas molecules, then basically that gas molecule container be defined as the thermodynamic system. Okay, so the first type of thermodynamic system is isothermal system. Okay, isothermal. Okay, isothermal system means iso means same, therm word is related to temperature, so same temperature. So if there is no variation in temperature, that is if delta T or dt, or you may say delta T is equal to 0, then at that time the system is regarded as isothermal system. Similarly, another is adiabatic system. Adiabatic system. Okay, adiabatic system means this is related to heat energy. If there is no change in energy, in case of isothermal, there is no change in temperature of the system over a time or over the process, and in here no change in heat, no change in heat. Okay, so this is no change in heat. This deals that dq equals to 0 in the system. Okay, so similarly we can move on. Isobaric system. So isobaric means this word you can just figure out from there's a root word like iso means same. So this baric word is coming from the term related to barometer. That's why we can easily understand this is the system with no change in pressure. Okay, no change in pressure. If there is no change in pressure, then this kind of system, that is dp equal to 0. So this kind of system is called uh, isobaric process, isobaric system. Similarly, there is another, that is isochoric. Okay, isochoric system, isochoric process. So isochoric means choric means related to volume. So if there is no change in volume of the process, okay, there is no change in volume, then this process is called isochoric process. So that is dv equals to 0. In system there is no change in volume. So if you know these things, then from here you can ultimately bring some kinds of conclusion, like if there is no change in temperature, then this type of system will be very slow, because to maintain constant temperature the process should be very slow. These processes are slow process. Okay, so this is your too much slow process. Okay, but in the meantime, adiabatic process. So if you don't want to change the heat energy in system, no matter you cannot accept the heat, and even you cannot reject the heat to the surrounding, then without exchanging heat, then this kind of system should undergo very rapidly. So this is very rapid process. Okay, or very fast or sudden. This is very sudden process, the bursting of the tube, inflated and others. Okay, similarly, then in this isobaric process, pressure is constant. So if pressure is constant, then in here the work done can be. But in case of your isochoric system, there is no change in volume. There is no change in volume. That's why in this case, work done is also 0. In here, work done is 0. But in here, work done will be, there will be certain amount of work done. So in this process, furthermore, in this process, you will receive no change in temperature. That's why if you take ideal gas, then all the heat energy that you have been supplying, or even if you have been taking out from the system, the temperature is not changed. That's why in this process, change in internal energy will be 0. Okay, no internal energy will be changed, because internal energy is the function of temperature for the ideal gas basically. Okay, in here the process is sudden, and we haven't supplied the energy in the system to do work. That's why in here work will be done in cost of internal energy. Okay, all the amount of work will be done in cost of internal energy. That's why in this process, temperature final will always be less than temperature initial, because in cost of internal energy the work will be done. That's why the final temperature will be smaller. Okay, so this is the general idea about the different kind of system. Now let us talk about the work done by the gas in system. Okay, so we know well, so work can be calculated as the product of change in pressure and change in volume, or sometimes we can write dw. Okay, dw equals to how much? The force into displacement. Okay, force times displacement. Okay, even this force can be written as, this force can be written as pressure times change in area. Okay, or no, not change in area, pressure times area into displacement. So if you simplify this, then from here you can easily get, this is pressure times this area into del x, that is change in displacement, or that is change in the position. So this gives you dv. Okay, this is how you can get the work done. Okay, so if you have a very small change in the volume, and if it takes very long time, then you just can calculate the work done in the form of integral, that is integration of pressure to change in volume from volume v1 to volume v2, where the pressure is constant. Okay, so this gives you the idea of the work done as well. So another important thing that we can include in here is PV diagram or indicator diagram. Okay, this indicator. Okay, indicator, indicator. Okay, there is something wrong with this. Okay, let me write again. Okay, something is gone wrong. I'm just fixing it. Okay, so in here the indicator diagram. Okay, indicator diagram simply means the plot between pressure and volume. If you have a plot between pressure and volume for the given system, then this is your PV diagram. So from PV diagram also we can find out the work done. Okay, so for example, suppose this is your PV diagram, this is your V and this is your P, and if you have a curve like this one, then if you calculate the area under this curve like this one, so this is your curve, how much area is included by the curve below. Okay, so this is your uh, area under the curve. This area under the curve also gives you area under the curve. Okay, this also gives you the value of work done. Okay, so from different way we can calculate. You can calculate like a PdV or dW equal to V1 to V2 PdV and so on. So this also gives you the idea. So work done. Okay. Further, there are different processes like a cyclic process. Okay, reversible process, irreversible process, and so. For the reversible process. Okay, reversible process. Okay, in reversible process, let us figure out work done. Okay, so in reversible process, for your simplicity, I just want to draw a diagram. This diagram is so useful while dealing with the work done. Okay, this is your pressure and volume. For example, your process is reversible. Let's say uh, the process is started from here and it has gone this way, and if the process will come back from the same region like this one, the process is reversed back through the same path, then you can just see from the area under the curve with this green color and the area under the curve due to red color are equal. Okay, and work done from this first to second can be taken as positive and second to first can be taken as negative. That's why overall work done in this reversible process. Okay, in this reversible process work done will be 0. Okay, so but if you have a process, irreversible process, cyclic but irreversible. So if you have irreversible process, for example, let's say this is your V and this is your P, and let me just draw with a different color. Suppose your system runs from this 1 to 2, and if it goes back from 2 to 1, this is a reversible process, cyclic process. So in this case, there is a net amount of work done. So the area under the curve with this blue color is this much. Okay, this much. And area under the curve due to this pink one is more. That's why if you just take the difference between this area due to pink color and this due to blue color, then you will definitely find the work done is greater than 0, or this work done is not equal to 0, as if in the case of previous one. Okay, now let us move on and discuss the other ideas. Okay, so if you have the isothermal process, okay, so in isothermal process, if you want to calculate the amount of work done, then you can simply do dW equals to integration of V1 to V2 and P dV. So this gives you the work done. And you know well from the equation of state, PV equal to nRT. So if you just do integration V1 to V2 and from equation of state PV equal to nRT, you know P equal to RT by RT by RT by B. Okay, and even the term n will remain in here, and it is your V. If you integrate this process in mathematics, then you result into work done equals to nRT logarithm. This is a natural logarithm V2 by V1. Okay, the final volume minus initial volume, or sometime this is your nRT ln P2 by P1. Oh, sorry, P1 by P2. They are inverse to one each other. That's why you can easily find P1 by P2. Okay, so this is the work done in case of your isothermal. Okay, so this is the idea of isothermal process and the work done. Now let us look at some idea related to adiabatic process, and even we will calculate the amount of work done in adiabatic process too. Okay, so from the equation of state of adiabatic process, you know well, you can easily develop this relation for adiabatic process. For adiabatic process, okay, equation of state can simply be written as PV gamma equal to constant. Okay, this is one form. Similarly, we can write in the other form as well. Okay, so TV gamma minus 1 equal to constant. Okay, similarly in terms of pressure and temperature, P1 minus the gamma T gamma. Okay, T gamma equal to constant. So these are the equations of state. So utilizing this PV gamma equal to constant, the work done in this process, work done in the adiabatic process can easily be calculated. Okay, so in adiabatic process, okay, so let us figure out this adiabatic process work done. Okay, work done in adiabatic process can easily be calculated as nr divided by gamma minus 1. Okay, gamma minus 1 T1 minus T2. Okay, be careful with this one, T1 minus T2. In adiabatic process, no heat is supplied. That's why all the work will be done in cost of internal energy. That's why your initial temperature will be larger than that of the final temperature. That's why initial temperature comes first here. Okay, so this is the work done in case of adiabatic process. Okay, so this is the general idea. Now we will be discussing some general idea about the different type of heat capacities. You know well, specific heat capacity. Specific heat capacity means amount of heat energy required. Amount of heat energy required to increase the temperature of 1 kg of substance by 1 degree C. This is a well established thing for the case of uh, solid and liquid. This is well defined, but in case of gas this is a bit difficult. Specific heat capacity with unit joule per kg per degree C. Okay, this is well defined, but in case of gas this is a bit difficult. Sometime we can keep the gas in constant pressure, sometime in constant volume. That's why for the case of gas we will be defining the other term, other thing, that is basically called uh, molar heat capacities. Okay, so these molar heat capacities can be defined in two ways. That is, one, molar heat capacity or molar heat constant, that is called at constant pressure. Okay, so let's say CV. So when you are supplying heat energy, and that supplied heat energy is being utilized at constant volume, then all the heat energy will be utilized to increase the internal energy. Okay, so because in constant volume there is no change in volume, so no work is done. That's why whatever the heat energy you supplied, all the supplied heat energy will be utilized to increase the internal energy. But in the other case, if you are just supplying heat energy in constant pressure, this supplied heat energy will be utilized to increase the internal energy, as well as while maintaining constant pressure it does some work. That's why, see, if you supply some amount of heat energy that solely increase the internal energy, then definitely this magnitude will be less, or CV will be less. In here both the things is happening. दुईटै केसमा टेम्परेचरको चेन्ज कति छ, 1 छ। ओके, यसलाई अलिकति यसरी मजाले बुझौँ। मानौँ यो हाम्रो कन्स्टेन्ट भोल्युम केस हो। ओके, सो सपोज गरौँ यो हाम्रो कन्स्टेन्ट प्रेसरको केस हो, यो प्रेसरको केस। ओके, सो प्रेसर कन्स्टेन्ट छ, यसको मतलब जरुरी छैन कि भोल्युम बढ्दैन भनेर, भोल्युम पनि बढ्छ। यो केसमा पनि हामी 1 डिग्री बढाउने हो, यो केसमा पनि 1 डिग्री नै बढाउने हो। ओके, सो यसमा चेन्ज हुने इन्टरनल एनर्जी र यसमा चेन्ज हुने इन्टरनल एनर्जी चाहिँ बराबर। तर यो केसमा जम्मा के भएको छ, here is only increase in internal energy. So whatever the heat you have supplied, all the heat supplied will be utilized to increase the internal energy. Okay, but in here supplied heat energy will be utilized to change the internal energy as well as doing some work. It does some work as well. That's why this magnitude, this q dash must be greater than q. That's why here what we can say is this Cp is greater than Cv. And if you simplify these terms with the help of this thermodynamic system, then Cp minus Cv will be equal to the universal gas constant. Okay, it will be equal to universal gas constant R. Okay, so this is your universal gas constant R. And even if you take the ratio of Cp to Cv, Cp to Cv, in this case as well, you will be getting one ratio that is called gamma, and its value is 1.42 for diatomic gas and 1.6 for monoatomic gas. Okay, so this is all about the general idea of this first law of thermodynamics. Now we will be moving on to some previous year questions from medical and engineering entrance examination. So let us move on to that one. Okay, so in here there are some questions that have been asked in previous examination. So let us look at the question and let us crack this question briefly. Okay, so the first question is, the pressure and volume are changing. Okay, but the temperature of the system is fixed. The process is called, this is isothermal. Pressure and volume and changing, temperature is fixed. If temperature is fixed, the system is isothermal. This is so simple, you can easily answer this type of problems. Okay, so the internal energy of the system depends upon, I previously told you, internal energy is solely a function of temperature. Basically for the case of ideal gas, all the time we will be dealing with ideal gas. That's why this internal energy is the function of temperature. That's why our answer is directly temperature only. In an inflated bicycle tire burst, which of the following relation holds good for the pressure and temperature? So and inflated bicycle tire burst, so this simply suggests us that this process is very shortened, and this process is adiabatic. So in adiabatic process, pressure and temperature are varied as P power 1 minus gamma, okay, and T power gamma, okay. So where the relation is there, 1 minus gamma. So P power 1 minus gamma and T power gamma. This is the direct answer. So you have to remember all the three equations of state of adiabatic system, PV, TV, and VP. Okay. So here another. So question number 4 says you the energy of molecular motion is, okay, the energy due to molecular motion. Molecular motion ले कस्तो खालको energy दिन्छ. Okay, so basically in case of gas, molecular motion and the interaction between the molecules gives us the internal energy. Okay, so molecular motion ले kinetic energy दिने भयो, अनि molecule को बीच interaction ले potential energy दिने भयो. So यहाँ basically molecular motion भनिसकेपछि interaction को कुरा छोड्ने हो भने mostly kinetic energy हुन्छ, तर कुनै पनि सिस्टममा भएको मलिक्युलको काइनेटिक एनर्जीले इन्टरनल एनर्जीलाई एडभोकेट गर्छ, किनभने काइनेटिक एनर्जी डाइरेक्टली करेस्पोन्ड गर्छ टेम्परेचरसँग पनि है. व्हिच वान क्यान बी रिभर्स्ड ब्याक इभन क्यान नट बी रिभर्स ब्याक. दिस इज भेरी इम्पोर्टेन्ट. क्यान नट बी रिभर्स ब्याक इभन थ्योरेटिकली विदाउट डुइङ वर्क. ओके, सो कुन सिस्टमलाई चाहिँ वर्क नगरिकन हामी पछाडी फिर्ता ल्याउन सक्दैनौं थ्योरेटिकली पनि. यहाँ हेरौं आइसोथर्मल केसमा के हुँदो रहेछ, एडियाबेटिकमा के हुँदो रहेछ. इफ वी क्यान फाइन्ड देन वी क्यान इजिली फिगर आउट द आन्सर. ओके, फर एक्जाम्पल दिस इज योर सिस्टम. सो आइसोथर्मल एक्सपेन्सनको केसमा के हुन्छ, हामी हिट सप्लाई गर्छौं, यो यहाँसम्म चेन्ज भयो सिस्टम. So if you want to reverse it back, then you have to do work from outside. Without doing work, you cannot come back to original state. Okay, you cannot come back without doing this work. So compress गर्नु पर्यो. Compress गर्ने हो भने you must do work to come back to the original state. Okay, so that's why in case of the correct answer is isothermal expansion, adiabatic expansion, adiabatic compression, and isobaric expansion. So adiabatic मा हुन सक्ला, isobaric expansion मा पनि हुन सक्ला, हामी आउन सकौंला theoretically. But in case of isothermal expansion, expand भयो, contract. Isothermal contract गर्नको लागि के चाहिन्छ, we must do work against of gas molecules, and then only we can come back to the original state. Okay, so let us move on to another. If a gas is allowed to expand adiabatically against the external pressure, okay, then its temperature remains same. Adiabatic process ma expand huna payo भने temperature त घट्छ, because work will be done in cost of internal energy. Okay, यो त भएन क्यारे. Pressure remains constant, यो पनि pressure change होला कि. There is increase in internal energy. Internal energy increase हुने चान्सै छैन, बाहिरबाट heat energy supply छैन. There is decrease in internal energy. This answer is correct, because in cost of internal energy the work is being done. That's why the internal energy will decrease. Okay, so now let us move on to other questions. Okay, just before this I just want to remove the ticks of previous answers so that it will be quite easy for us to deal. Okay, so these are the other questions. So in here, in which of the following work done is maximum in the expansion? If there is expansion, then which one will have maximum work done? For this one, this graph is so useful. Okay, so this fourth is isobaric process, constant pressure. This is isochloric process. This is this is isothermal process, and this one is adiabatic process. Okay, so यो केसमा हेर्ने हो भने for the case of this isobaric, the area under the curve is maximum. That's why from this diagram it is so clear that in case of isobaric process the work done will be maximum. Okay, next, The internal energy of the ideal gas depends upon, it is the function of temperature. So from the understanding, you can directly write, even you don't need to observe for the case of ideal gas. Okay. Next, which when water is heated from 0 degrees C to 4 degrees C, which one holds good? Okay, so constant pressure, constant volume, specific heat capacity or molar heat capacity, pressure, and constant volume are there. It is not always necessary that Cp will be greater than Cv. Cv will be greater than Cv. We cannot say, but in case of your 0 to 4 degrees C, volume is decreased, but temperature is increased. Internal energy is going to be increased. That's why that will nominalize one each other, balances one each other, and directly you can remember the answer as this one. Okay. If 1500 calorie of the heat is supplied to the system and 1000 joule of work is done, then increase in internal energy. This is quite a different kind of question. Here is in calorie, here is in joule. That's why first of all you need to calculate this in terms of joule. This is around 6300 because you have to multiply in here by 4.2. Okay, so if you just do the calculation, then I believe you will come around this 5000, or if you just do 4 only, then this is 6000. 6000 minus 1000 is 5000. So more better answer is 5300. Okay, so this answer is more correct. From the diagram alongside, name the adiabatic process. Okay, this question is so crucial. You can easily determine which one is isobaric, which one is isobaric, but the two curves, this 3 and 2, are quite similar. So one thing you have to remember is the slope of the adiabatic, okay, I just write here, slope adiabatic is always greater than slope of isothermal. So in this case, the slope of this 3 and slope of this 2, obviously slope of this 2 is so steeper. That's why the curve 2 must represent the adiabatic process. Okay, this is what your answer in here. Finally, we have two more questions. In irreversible process, okay, the process is irreversible. In irreversible process, in change in internal energy, it could be change in internal energy is 0. Let me just draw the diagram. Suppose this is your irreversible and cyclic process. Okay, so okay, this is irreversible and this one is cyclic. Irreversible and cyclic process. In here, change in internal energy is 0. Irreversible, in here cyclic. Okay, this question help. Cyclic. Okay, irreversible cyclic process, change in internal energy is 0 because they will be at common temperature. Work done is not necessary. Okay, so work done may not be 0. Both A and B, and cannot be determined. So in here, work done, okay, work done is equal to 0. Okay, this is not a cyclic process. I believe this question should not have a cyclic process. This is only irreversible process. Okay, still I believe there is an issue in this question. This should be reversible process. Then I see this answer is going to be correct. Okay, for reversible, then this B, A, both A and B will be correct. Okay, A and B. So next question is the unit of molar heat capacity is. This is your specific heat capacity, not molar heat capacity. This itself is wrong, nothing. Joule per mole per degree C. And this looks so correct answer. And per mole, per kg, per degree C. This kind of formulation will not be C. Molar heat capacity means per mole, how much heat energy is required to increase the temperature by 1 degree C. So that's why amount of heat energy required to increase the temperature of 1 mole of substance by 1 degree C. So this is what your correct answer. So in this video lecture, I have discussed about the different questions from previous entrance examination and the general idea of first law of thermodynamics. So I will be following up with second law of thermodynamics in next lecture. Okay, and stay tuned us for the different kinds of updates and questions MCQ from different chapter, and don't forget to subscribe, share, and like our videos. Thank you.